Okay, hi, AP statisticians, mathematicians, anyone else who somehow tragically stumbled upon this channel. This is Mr. Pinto here, and I've got a different setup for this semester. I used to just record over the .cam, but for this semester I'm going to be doing a little bit more integrated technology because we're still in hybrid learning, because there's still a pandemic going on. So I've got my calculator. I'll make sure to do some of my calculator commands on the screen so that you can see what's happening there. A digital pen, some erasable pens, and then we have basically the last half of AP Stats ready to go here. So now you can hear my face and see my voice. Or the other way, you know, one of those. But you will get to now see all the live bloopers and all the facial reactions that I make during what is called these virtual lessons. So in the second half of AP Stats, we're going to be dealing with inferential statistics. The first half was descriptive statistics, so we looked at collecting data, describing data, univariate and bivariate data, categorical versus quantitative data, and then we wrapped up with probability and random variables. Now, we're going to take all of that, and that's been building up to the main goal of statistics, which is inferential thinking and inferential statistics. Essentially, what are we going to do, right, based on the information we have? How can we use this to predict or infer different things about our population based on a sample from which we've pulled? So we're essentially just trying to put the pieces together. We might not have all the information, but theoretically we should have sufficient information to build this picture. So the first thing that we're going to need to do is we're really going to look at the difference between quantitative and categorical data. So here you can see on my screen that we're going to be looking at inference for proportions for this first section of inferential statistics. Now, proportions deal with categorical data. So we're going to start with the sampling distribution for proportions. So a parameter here is basically what we call a characteristic of the population. And I feel so self-conscious looking at my eyes here and over here, but oh well. And a statistic is a characteristic of the sample. So we use parameters for the population, and we use statistics for the sample. Now, because this is categorical data, we are going to, I can't find all my colors here. Where are all my colors? Okay, update, I found the colors, and I found out I can actually pause in between the video and pick it back up. So y'all, this is really going to be a fun semester. But because we're looking at categorical data, we are going to use P, which that was a terrible P. Okay, so mulligan, you know, I'm just going to keep the bloopers in for you all to actually enjoy the comedic relief that is virtual learning. So here, the characteristic of the population we're going to look at is P, which is the population proportion, and the characteristic of the sample will be P hat, which is the sample proportion. Now, we need a few key pieces of information when constructing a sampling distribution for P. Now, for example, samples vary, and that's what we call sampling variability. Your sample would be different than my sample, than Johnny or Susie or anyone else who's taking a sample. So essentially, smaller samples have more variability, but the more samples we begin to take, the lesser the variability and the closer to the truth we can begin to approximate. A sampling distribution is now the distribution of values for the statistic for all possible samples of a given size from a given population. That means if our population were all adults in the United States and we somehow managed to take a sample of every single adult in the US and pull the sample proportion, which we're estimating for the population proportion, and we computed all of these statistics, we could estimate this true population parameter, this population proportion. That's very difficult and nearly impossible. In some cases it might be possible, but theoretically, we're not going to get the full true sampling distribution, but we're going to get an approximation of the sampling distribution. And then lastly, we're going to look at the central limit theorem. We'll be doing an activity in class to verify this. Sorry, online students, but these, remember, are just summary videos, which are the notes portion of the course. All right, so the CLT, or the central limit theorem, tells us that when the sample size is sufficiently large, a sampling distribution of the mean, or proportion, of a random variable will be approximately normally distributed. So again, this idea that the more and more samples we take, the closer to the truth we get. In order for this to be applied for proportions, they must be independent of one another in addition to n being sufficiently large, and this is what we call the 10% condition. Now, we have 4 types of estimators. The first estimator is malo, very bad. You can see that this distribution here is very spread out, and it actually doesn't capture what we're seeking, the population parameter. So this is high bias, which means we've missed the parameter, and high variability, which means that we haven't circled in, or we haven't really honed in on where that parameter is. So this is a bad thing. We do not want this. Next up, though, and our goal is this pretty picture here. There's low bias, meaning we most likely used a random selection, or sorry, a random sampling method to estimate the parameter. And there's low variability, which means either we took a sufficient amount of samples, or the samples we took were just very close to that original parameter. So this is what we want. And then the bottom 2 cases are essentially, am I moving myself? I don't know if I'm moving myself. All right, so what's happening now is that these 2 bottom ones are also bad cases. So in this one here, we can see that there is low variability, but there is high bias because we miss a parameter altogether, but the distribution is relatively close. Here we have low bias, but we have high variability. So you can see that these are the 4 combinations between bias and variability when we're looking at estimators of this parameter. Now, for proportions, since we're looking at the sample proportion, we are going to use p hat. So here we go. I'm going to use p hat, which is our sample proportion, and the way we calculate this is going to be x over n. Now, x over n, x is going to be the frequency, or what we call the number of successes. So, and remember from the binomial distribution, a success isn't always a good thing. A success is just, it just means that the event occurred. And then n, we're very familiar with, is going to be our sample size. Not the number of samples, but the number of objects within a sample. So there's a difference between the number of samples and then your sample size. So our main sample statistic for this unit will be p hat, which is the sample proportion, which we are using to estimate p, which is the population proportion. So let's actually take a look here at constructing a sampling distribution for p so that we can do some calculations and do some inference. Now, suppose we have this population of people, and this population can be live people, it can be inanimate objects. Essentially, it is all the members who belong to this specific group that you're looking to research. So within this population, there exists some p, which is this population proportion. Maybe it's the number of cars that were manufactured in the year 1988. Maybe it's the number of people who have brown eyes, or maybe the number of people who are right-handed. And notice that the variables I'm listing are all categorical variables. Each of these people belong to a specific group in this population, or have a specific success or characteristic from this population. So in order to get a good estimate, we take some simple random samples of size n. So that's to say we're taking a sufficient amount of samples, and these ellipse here just means that it continues on. And we're taking the sufficient amount of samples, and ideally they're all the same sample size. So samples of 30, 50, 100, 1,000. It doesn't matter how many samples. Okay, never mind. It does matter how many samples because the more samples, the closer you get. So essentially, you just need to make sure each time you take a sample, it's the same amount. So we take samples of size n, and each sample produces its own unique p hat. So sometimes they might be the same, sometimes they might not be the same. And again, that's due to the sampling variability that's present from sample to sample. And we notice that if we had an infinite amount of these samples selected, we would get the following picture. We notice that the shape of this distribution here appears unimodal and symmetric. We can see the center happens at the mean, which is p, the population proportion. And then we see here that the spread of this distribution is the square root of p times the complement of p over n. And so where do each of these values come from? Well, they all come from a necessary condition in order to construct the population parameter. So the first condition that we have to have is that it is stated random. And so I'm actually going to switch to typing here. Now, there are 2 types of random methods we could use. So the first one would be a random sample, and the second one would be a random assignment, assuming this is an experiment. So I'll type that in as well. And we learned back in Unit 3 that if we have a random sample, that will help us to generalize to the population, and that will also help us to reduce the effects of bias. Next, if we have random assignment, this helps us to infer cause and effect, as well as, oh, I lost it. Where did it go? Cause and effect, plus it reduces the effects of confounding variables. So sorry, kiddos. I hope you can all fit that in the same box. I'm kind of cheating because I get to type, and you all know that stats is a lot of writing, but oh well. Okay, so that's our first condition there, is that it must be stated random, whether it's a random sample or a random assignment. So the way this table works is that the condition and how we meet it, or here's the condition, here's how we meet the condition, and here's why we need the condition. The next condition is the condition of independence, and there are two ways to meet this condition. The first way is, oh, I got this little audio box here. So the first way is, right, is that the results do not influence one another. And the second way we meet this is that we use the 10% condition. And the 10% condition says the sample is less than or equal to no more than 10% of the population. And that's a very ambiguous number. I do not know why it's 10%, but essentially, if it's less than 10%, we can assume that my sample and your sample, if they're both less than 10%, would have no influence on one another. And that actually brings us to why the condition must be met. And the condition must be met so that the degree of dependence, why can't I spell? The degree of dependence is negligible between observations. All right, and I've got about 3 minutes left, so I'm going to speed this up a little. And lastly, we want them to be approximately normal, and we do that by, and I'm actually going to write this one in. This is what we call the large counts condition. So this is large counts, which says the following: n times p must be greater than or equal to 10, and n times 1 minus p must also be greater than or equal to 10. And if those conditions are satisfied, we can say that the sampling distribution is approximately normal by large counts. And the reason we need this condition is so that we can assume the sampling distribution is approximately normal. And actually, I'm shorthanding here, approximately norm, so we can conduct the correct inference procedure. And that procedure could be the sampling distribution, it could be a confidence interval, or it could be a hypothesis test. So we need that normal approximation so we can correctly calculate the test statistic, the interval, the p-value, etc. It all is kind of building into this puzzle here that is inferential statistics. So those are our three conditions, and you notice SIN, we can say that our three conditions are sinful, stated random, independent, and normal. And that's your terrible stats joke of the day. So the last thing here is that if these three conditions are met, then we use the following parameters. So the shape would be approximately normal. And okay, so this will be approximately normal by large counts. And I'm just going to abbreviate some here. The center would say that the mean of our sample proportion would actually be equal to the population proportion, because if we're using some randomization method, we should have a low amount of bias, so it should capture the true parameter. And then lastly here, our spread, where am I? Oops, sorry, did not mean to do that. Okay, you don't need that. I'm running out of time here. The sigma of p hat, standard error, or the sample standard deviation of the population proportion, or here of the sample proportion, is equivalent to the square root of p times 1 minus p divided by n. And we'll talk a little bit more about these conditions in the following example. So if the three conditions are met, stated random, independent, normal, then we should have these three characteristics of our sampling distribution: approximately normal, a center at p, and then a spread of the square root of p times 1 minus p over n, and take the square root of that.